contract has been signed, and if you'd like to sign it, Mr. Undertaker, you may. Oh my God!
All right, gang, welcome back. This is the problem that we left on last time. So we've got these two 2-ohm resistors and these two 4-ohm resistors. Each of these are connected to one another in parallel, but the whole circuit is run in series. So hopefully what you're able to figure out is that this circuit, we can make an equivalent version of it that looks like this, where we've just squished each of those parallel bits together. So, as you can imagine, this could, in theory, be frustrating if these values were something annoying to plug into that equivalent resistance formula, but because they have the same value, there's actually a little trick that we can use. And it works like this. For resistors that are in parallel, if the resistance values are the same, we can just take that resistance value, and our REQ is going to be that number divided by how many you have. So let's make that look more like how it's supposed to. REQ is going to be R divided by how many resistors that you have. And in series, REQ is going to be very similar. It's just going to be the number of resistors that you have times that R value. So for the setup that we have, we've got two 2-ohm resistors. So it's going to be 2 divided by 2, or just 1 ohm. And just as a check, in case you don't believe that that formula works, 1 over REQ is equal to 1 over 2 plus 1 over 2, just the old formula that we've been using this whole time. So we're going to have 1 over REQ is equal to 1, and the inverse of that, 1 divided by 1, is the same as 1 divided by 1. So that trick will work, and we know that that equivalent resistance has to be 1. Using the same logic, we've got two 4-ohm resistors. So we're going to take 4 divided by 2, and so this will be 2 ohms of equivalent resistance. Nice. So now we can fill out our grid just like we've been doing before. Not a problem figuring that out. So we're just going to figure out what that total equivalent resistance is and use that to get a current. So our total equivalent resistance should just be the sum of these two numbers. 2 plus 1 is going to give us 3. So the total equivalent resistance is 3. Then to find that current, we're just going to take our total voltage and divide by that total equivalent resistance. So 9 divided by 3 should give us 3. And that is going to be the current that goes into each of these. This one gets 3 amps, and this one gets 3 amps. And they'll each get the same because they're connected in series. Nice. So now we have to find each of their individual voltages. And the way that we're going to do that is just with Ohm's law. So we're just going to take our current times our resistance. 3 times 1 is going to give us 3 volts. 3 times 2 is going to give us 6 volts. And that should make some sense because we want all these voltage drops to equal that voltage gain. 6 plus 3 gives us 9. So everything is working out the way it should. But as is always the case, we've figured out things for the equivalent circuit. Now we got to work backwards. We got to figure out what's going on in the original circuit. So we got to figure out what information is going to carry back to our original setup. And the way that you do that is always going to be the same. We think about how we got to this point. What did we have to do to get this equivalent resistance? What we had to do was squish these two things in parallel. And so what is the same in parallel? It's just your voltage. So if this equivalent resistance gets 3 volts, that means each of these resistors got 3 volts. And if this equivalent resistance got 6 volts, each of these got 6 volts. So if we were to fill in this table over here, we would know that we have 4 resistors, R1, R2, R3, and R4. R1 has a value of 2 ohms, and it is going to have 3 volts. And so we know the current is going to have to just be Ohm's law, 3 divided by 2. I'm just going to leave it like that. And then we got to find R2, which is going to be this guy. And it's the same thing. 2 ohms, 3 volts, and the current is going to be 3 halves. Then for R3, which I'm going to call this top one, we know that this has a value of 4 ohms when we go back to our original circuit, but it's still going to get that 6 volts. And so using Ohm's law, 6 divided by 4, well, that's going to be Look at that, 3/2. And then R4 is going to be 4 ohms, 6 volts, 3/2 of an amp. As hopefully you'd expect, because this whole thing is in series, so it should make sense that they should each get that same 3/2 of an amp. So we've been talking about electric circuits for our distance learning that we've been doing, and we reviewed first of all current and resistance and Ohm's law and electric energy, and then we talked about series and parallel circuits, and now we can move on to Kirchoff's laws. And so the whole idea of what we've been talking about so far is that circuits are a way to use current to do some kind of electric work, either to light a light bulb or power a computer or whatever it happens to be. And there's a couple of different ways that you can combine those resistors together in order to do that work. So in series, you have a setup where all of your resistors have the same current, but they each share the voltage that you get from the battery. Or you could connect things in parallel, where now you have things that are connected with different currents, but all with the same voltage. And there's even a way where we can put them together where we have some things in series and some things in parallel. But if we go back to the basics of all of this, the purpose of the battery, why that was the thing that was giving you energy for this whole setup. And then over each of the resistor's job was to use some of that energy to do some kind of work. And at a junction in a parallel circuit, you had current branch off from one path to another. And so this dapper devil up here, Gustav Kirchhoff, came up with Kirchoff's circuit laws, and we have to be sure that we're calling them his circuit laws because he had a bunch of other things that he worked on. And they're just another way of explaining these simple ideas that we already talked about with circuits. Understanding that energy gained by the battery is what's used over the resistors, and that current has to be conserved, can give us these two formulas right here, which we call together Kirchoff's laws. He's got the junction rule, or Kirchoff's current rule, and all that says is that currents coming into a junction have to equal currents leaving a junction. That's just conservation of current. Whatever comes in has got to equal whatever comes out. And then you've got Kirchoff's voltage law, which is sometimes called the loop rule. And it's the same kind of idea. Whatever the voltage gain is over the battery has to equal the voltage drop over each of the resistors. Okay, so if Kirchoff's laws are actually laws, then they should hold for even the simple circuits that we talked about already. So let's just take a simple series circuit and let's see if Kirchoff's voltage law, the loop rule, works. So we've got 120 volts for our power source and two 100 ohm resistors. We can solve this just with a simple grid like we've been doing before. So we'll put in everything that we know, just like that. And then the next step, of course, is going to be to find that total resistance, which is going to be our 200. Then we just have to find our current using Ohm's law. So that's just going to be 120 divided by 200, which is going to be 6/10. And because it's a series circuit, that's true everywhere. So this will also be 0.6, and this will also be 0.6. And then we just have to multiply using Ohm's law, current times resistance, to get these voltages. So that's 60 and that's 60. And as a check, 60 plus 60 gives us 120. So that's just review. That's everything that we know. Now let's see if we can get the same results using Kirchoff's voltage rule. And so this is the way that it goes. We have to figure out what the voltage gain is. And that's just what the battery supplies. So if we start on this negative side of the battery and move through it, all of those charges that are moving through the battery are getting a push from that battery, and they're getting exactly 120 volts worth of a push. So we would just call this 120. And then those charges, they're just going to move through this wire, and they're going to get to that first resistor, and they're going to lose some voltage from that first resistor. So they're going to lose whatever V1 is, whatever the voltage drop is over that first resistor. And then they're going to get to the second one, and they're going to lose some voltage over that as well. And by that point, they've lost all the energy that the battery supplied. And so that difference should sum up to 0. If it didn't sum up to 0, that meant there was some other loss of energy somewhere. But these V1 and V2 terms, we can replace those using Ohm's law just like this. 120 minus I1 R1 minus I2 R2 equals 0. Okay, nice. But we also know that because this is a series setup, I1 and I2 are really the same. We can just call them I. So I'm going to make this 120 minus I times R1 plus R2. I just pulled that I term out, well, really the negative I term out, and so that's why we've got that plus in the middle. And so now we've got an expression that really only has one unknown in it. We just don't know I. So this is going to become 120 is equal to I times 100 plus 100, just moving that over and plugging in what we know. And so then I is going to be 120 over 200, which we already found to be 0.6 amps, like in the grid over there. We've got a simple parallel setup, 120 volts connected to 100 ohms and another 100 ohms. So just a simple 2 resistor parallel circuit, just like we've done before. Let's try and see if we can get our answers with the grid, just like we did on Tuesday, and then we'll verify it with this junction rule, with Kirchoff's current rule. So, as always, we're just going to plug in our knowns first. So we know that each of the resistors is 100, and we know the total voltage is 120. And so on Tuesday, we always wanted to just carry that voltage across because it would make our lives easier by not having to do that equivalent resistance formula. You still can, but we've got nice numbers this time. We know that these two resistances are the same, so we can use our trick that we just learned. We can take this resistance value and divide by how many we have. So that's going to be 100 divided by 2, which is 50. Then we can carry this 120 across. And then finding these currents is going to be very easy. It's just 120 divided by 100. So they're each going to be 1.2. And if we sum these up, we've got 1.2 plus 1.2, which is 2.4. And I think that 120 divided by 50 is 2.4. So hopefully somebody will double check that for me. So this is our setup with the grid for this parallel circuit. Now let's see if that matches what we get with Kirchoff's current rule. And the way that this current rule, or this junction rule, works is we have to look at one specific junction. I've kind of made them big bold circles on our picture here. So if we look at that top junction, we've got current that's coming in, which is this arrow right here. So that's the current coming in. And then we've got current that's leaving. So we've got one that goes through that first resistor and one that goes through the outside. So we've got one that goes that way and one that goes that way. It's a pretty awful arrow, but I think you get my point. So we have current coming in and then two that leave. And so we have to figure out what that current coming in actually is. That's just the current that came from the battery. So we could consider that current in as really being like an I total. And then we have to subtract both currents that are leaving. One goes through the first resistor and one goes through the second resistor. And they again have to sum up to 0 because otherwise current wouldn't be conserved. So just like with the voltage rule, they have to sum up to 0. But if we hadn't done this table, we wouldn't actually know anything about I total or I1 or I2. All the problem gave us was information about voltage and resistance. So we need to use Ohm's law to sub in for each of these so that it's only in terms of the stuff we know, just those voltages and resistances. So this is going to become V total over R total is equal to V1 over R1 plus V2 over R2. So all I did was move I1 and I2 to the other side and then plug in for Ohm's law. So now we've got V's in the numerator of each of these, and we know that we have a parallel setup, so each of these voltages are the same, so we should be able to just get rid of them. And we're left with a formula that looks pretty familiar. That's just our equivalent resistance in parallel. So all that we've done from here is we've shown that using this junction rule, we can get down to this law for equivalent resistance, and we already know that this is true. And you can go through and do the work, and you can find that 1 over R total is equal to 1 over 100 plus 1 over 100, which is 2 over 100, or that total resistance is 50 ohms, which absolutely matches what we had all the way over there. So what we find is that these two laws, Kirchoff's current law and Kirchoff's voltage law, they really do the same thing for these simple circuits as a regular old grid would do. And, depending on how you feel about each of these methods, using the voltage law or the current law could really be overkill for these problems. If you've got a simple series setup, there's not really a reason to use the voltage law for a setup like this. You could just as easily do it with the grid or in your head, depending on what those resistance values are for. So if you think about this, there's got to be some setup that makes these worthwhile. And so far we've talked about combining multiple resistors in series or in parallel, or putting the series and parallel combinations together, but we haven't talked about would be a more complicated setup, like if we had multiple batteries. And that's where these rules really are a necessity. We need to use Kirchoff's junction rule and Kirchoff's loop rule to solve something like this. And the way that we're going to do that is we have to essentially follow this recipe that Kirchoff set up from these rules. And as long as you follow these steps, you're going to get to a system of equations, which is not always the nicest to solve, but it will always get you the right answer. So here are the steps that we need to follow to use Kirchoff's rules for a complex circuit with multiple batteries. The first thing, as always, is to draw your picture, and you need to make sure you label everything. So all your voltage sources and all your resistors, they have to be labeled with numbers. Then you want to go through and find your junctions and label them with letters, starting at A and going through however many you have. And then you can draw in your loops. So you're just drawing either a clockwise or a counterclockwise arrow to describe which way you think the current is going to flow. And here's the nice thing about Kirchoff's laws. If you guess wrong on that direction, maybe current actually flows counterclockwise when you drew it in clockwise, it doesn't matter as long as you stay consistent. And what you'll find is that at the end of this whole game, you'll just get a negative answer, which is fine. You just know that you drew your original current arrow wrong. The magnitude will be the same. It's just going in the opposite direction. All right, so let's see if we can make sense of the first couple of steps in this Kirchoff game. So we've got our circuit drawn up here. I've got 2 batteries, 1 in each of these loops, and 3 resistors. One of them sits in the middle right here. And so the first thing that we want to do after we've drawn this picture is label everything. So each of these voltage sources, they get a label, V1 and V2. And each of these resistors, they're going to get a label, R1, R2, and R3. Nice. So now what we need is we need to label each of these junctions. So this one up at the top, I'm going to call A, and this one down at the bottom, I'm going to call B. So we've got 2 junctions, A and B, and then we've got labels for all of our resistors and voltage sources as well. And so then the next step is just to draw in our current loops. And so, generally speaking, current is going to travel from this positive side of the battery and then back to the negative, as long as we're talking about conventional current. And so a good guess would be maybe in this loop on the left, we've got some current which travels like this, and maybe the loop on the right, we've got some current that maybe travels like that. So we've got current that leaves from this battery and goes up and comes down, and current from this battery that goes up and travels through R3 as well. All right, so with everything set up, now we just have to figure out how to use Kirchoff's laws. And so I'll just write them in to remind everyone that our voltage gain plus our voltage drop has to sum up to 0. And then our currents into a junction minus our currents out of a junction have to sum up to 0. So that's the game that we're trying to play right now. We're trying to use these equations to figure out our voltages and currents over those 3 resistors for this more complex circuit with 2 batteries. So let's start with a loop, and let's do this loop that's on the left. So I'm going to call this loop 1. And what we're going to do is we're going to start at the battery. If you go through the battery the way conventional current does, from the negative side to the positive, that's a voltage gain, and so it's going to be positive. So I'm just going to choose to start at point B and travel along this loop. Where you start really doesn't matter. I think it's just going to be more demonstrative to do it this way. So I'm going to start at B and go up through this loop, and as we pass through that spot right there, we have a voltage gain. So I'm going to write in positive V1. Then we keep traveling along this loop and we get to R1. But as we travel through the resistor in the direction of current, we have a voltage drop. So this is going to become minus I1 R1. Then we have to follow this loop, so we're going to go down this path, and we're traveling through R3 in the direction of our loop. So this is going to become minus I3 R3, and then we're back where we started, so this is equal to 0. So that's loop 1. And we can play the same game with loop 2. So for loop 2, if I start at point B again and follow the direction that this loop is traveling in, I'm going to go along here, and I'm going to go through V2, and I'm going to have a voltage gain. And then I'm going to go through R2, where I'm going to have some loss, I2, R2. And then I'm going to go through R3, where I'm going to have another loss, minus I3, R3, and set that equal to 0. So all I'm doing is just summing up these voltages, where whenever I hit a resistor, I'm just replacing that voltage with Ohm's law. So this would be basically V1, current 1 times resistance 1. This is V3, and that would also be V3. So we have 2 equations, but we have a bunch of unknowns. We have all of these unknowns for this setup. So we're going to need some more equations to figure this out, and that's where the junction rule is going to come in. So let's look at junction A. If we look at junction A and our 2 loops that we drew, we essentially have this loop going clockwise, and so as this loop approaches A, it looks like that. And then as this loop leaves A, it does this. And then similarly on that side, if we follow this loop which goes counterclockwise, it comes up like this and then leaves down through the middle as well. Make this look more like an arrow. So at junction A, we have current from R1 and current from R2 coming into that junction, and then the current for 3 leaving. So we could write that like this. Maybe I'll stick with using the black marker. We're going to have I1 plus I2 is equal to I3. Everything coming into the junction has to equal everything leaving that junction. And we could do the same thing for B as well, but what you'll find is that for this problem, it's not super helpful. We're going to have I3 coming in, I1 goes that way, and I2 goes that way. So we just end up with the same formula. All right, so we've got 4 equations, and technically 5 if we use Ohm's law, and we've got 1, 2, 3, 4, 5 different unknowns. So we should be able to solve this. As awful as it is to have this system of equations, we should be able to solve this problem. And the method, there's a bunch of different ways to solve this because it's a system of equations. So as you know with systems of equations, there are plenty of different ways that you can solve them. Your substitution method, dividing your equations out, whatever you'd like to do. Here's one way to solve this setup. We know in our first loop equation that we have something with a 1, some things with a 1, and some things with a 3. And then our second equation, we've got some things with 2s and some things with 3s. If we replaced these ones, using our junction A formula, this top thing would only be in terms of 2s and 3s, and this bottom thing would only be in terms of 2s and 3s. So that's how I would like to approach this. Let's take our junction A formula. If we rewrite this solving for I1, this would look like I1 is equal to I3 minus I2, just moving that I2 to the other side. And so now we've got an expression for I1 that we can plug into. And we can just replace I1 with this right here. So using our loop 1 formula, keeping it in blue, loop 1 is now going to look like V1 minus I3 minus I2 times R1 minus I3 R3 equals 0. Hopefully you can see that and it didn't get too crammed on the sides. And so we can distribute this through if you'd like to, and you would get V1 minus I3 R1 plus I2 R1 minus I3 R3 equals 0. Okay, I had to plug my phone in, but now that we're back, we can see here that we have two things that are in terms of I3, that current I3. So we're going to combine them together, and we're going to make this V1 minus I3. And we pulled a minus I3 out of both of these, so this is going to become R1 plus R3, and then plus this middle term, plus I2 R1, and that's equal to 0. So we got a mess, but we now have something in terms of a voltage, I3 and I2. Just like our loop 2 formula is just a voltage, I2 and I3. So what we can do then is we can just solve this in terms of either I3 or I2 and plug it into the other formula to be able to get that one current that we don't know. At this point though, I think it's going to be easier to start working with numbers instead of all these letters. So I'm going to plug in the numbers that we had in the notes. So V1, the notes say is 10 volts. V2, the notes say is 20 volts, I think. Yep. R3 is 40 ohms. R1 is 10 ohms. And R2 is 20 ohms. So that's going to make our lives a little bit easier. I think it's going to be nicer to work with these numbers than with the letters themselves. It can get very crowded that way. So let's plug in what we have. We've got 10 minus I3 times R1 plus R3, which is going to be 10 plus 40, or as I like to call it, 50, plus I2 times 10, and that's equal to 0. And so now hopefully you can see there's a 10 here, a 50 here, which is just 5 times 10, and a 10 here. So if I divide 10 out of everything, our loop 1 formula simplifies down to 1 minus 5I3 plus I2 is equal to 0, or we can say I2 is equal to 5I3 minus 1. All right, so let's make sure that we take a second to not get lost in the algebra here. All we've done up to this point is a bunch of algebra, but it started from basic principles about circuits. We had this fairly complicated circuit with 2 batteries and 3 resistors, but all we did was say that as you go through one side of it, your voltage that you get from the battery is going to be used by each of these resistors, and the voltage you get from this battery is going to be used by each of these resistors. And then we also said that if you have a junction or a spot where multiple wires connect, the current that comes into the junction has to equal the current that leaves the junction. So all we've really said is that energy has to be conserved and that current has to be conserved. And then from that, we were able to work our way down to this expression that I2 equals 5 times I3 minus I1, So I'm just going to give myself a little bit more room here and copy my formula over. We said that I2 equals 5 I3 minus 1. All right. So now the question becomes, what are we going to do with this I2? Well, what I'd like to do is plug it into this loop 2 formula so that we can only have I3 as the only unknown for us. So I'm going to take our loop 2 formula, and I'm going to first plug in everything that we know. So we now know V2, that's 20. I2 times R2, which is 20, minus I3 times R3, which is 40, is equal to 0. And you should be able to see that we have some multiple of 20 in each of these. So I'm going to divide everything by 20, and this will become 1 minus I2 minus 2I3 is equal to 0. And so if I get I2 isolated by itself, I2 is going to be 1 minus 2I3. But what else do we know about I2? That it's 5I3 minus 1. So 5I3 minus 1 is equal to 1 minus 2I3. So I'm going to add that 2I3 over and add that 1 over. And so we're going to get 7I3 is equal to 2. Or I3 is equal to 2/7. So there we go. We have an expression now for what I3 is going to be. It's going to be 2/7 of an amp. So the current that travels through that middle leg is going to be 2/7 of an amp. And now that we've done all this work to get to this point, the floodgates are kind of open because we have expressions already for I2 and I1. So if we wanted to find I2, we already know that I2 is just going to be 5 times I3 minus 1. So this is going to become 5 times 2/7 minus 1. And so that's just going to be 10/7, like the stance, 10/7 minus 1, which is 7/7. And so we could say that I2 is equal to 3/7 of an amp. And then I1, well, I1 is just I3 minus I2. So it's going to be 2/7 minus 3/7, or negative 1/7 amp. And so we now have expressions for all three of our currents. We've got I3, and we've got I2, and we've got I1. And the only kind of sticking point that you may not like is that I1 is negative, but all that means is that this original loop that we drew for current 1 is going the opposite direction. It shouldn't be going clockwise. It should instead be going counterclockwise. And the reason why is now that we've plugged in these numbers and we've given these some kind of value, this 20-volt battery is twice as big as this 10-volt battery. So not only is this 20-volt battery going to push current down through the middle, this 20-volt battery is also going to force current the other way through this other loop. So you can think of this almost like a charging circuit. This 20-volt battery over here is pushing current through R3 and also pushing current through this battery, forcing current through it backwards in order to charge it up. And that's why this I1 ends up being negative. That 1/7 amp is correct. It is 1/7 of an amp of current traveling through R1. It just goes in the opposite direction. Then the last thing that you can do to round this problem out is you might want to find what each of these voltages are. So you could find V1, V2, and V3. And that's just Ohm's law. That's going to be I1, R1, I2, R2, and I3, R3. So that's just going to be 10 times 1/7 and that's going to be 20 times 3/7, and it is going to be 40 times 2/7. And just because fractions are nice like this, 10/7 of a volt, 60/7 of a volt, and 80/7 of a volt. Don't even need no calculator. And so it's a long, involved process, but this is how Kirchoff's laws work. You start out with your circuit, you make sure you label everything correctly, you arbitrarily choose the direction of your loops, you build your two formulas off of these two setups, your voltage law and your current law, and you just follow the algebra train until you get down to some currents. This takes practice though, and a lot of times it's a sign error that's hidden somewhere that's going to give you some issues. So definitely give these problems a try. There's another one on WebAssign this week that you can work with, and email me if you have any questions.